So welcome you back to today's module. So in the last couple of modules, we were discussing invariant testing. We realized that if my testing problem has a nice structure in the sense that my hypothesized populations are invariant under H0 as well as under H1 under a given group of transformations, then my testing problem is invariant. That means it has a nice structure. And that suggests I should consider only tests having a nice structure, which in this case amounts to considering only invariant tests. Now, invariant tests, if you impose the restriction of invariance, it reduces the data. That means it says you need not consider x1, x2, xn, rather you should consider some function of x1, x2, xn, which led to the concept of a maximal invariant statistic. So that means you should only consider the tests which are maximal invariant, and then find the best tests among tests which are maximal invariant. And we saw that in many situations we are able to get UMPI alpha test. Now we also noticed that invariance, by restricting ourselves to only invariant tests, we are reducing the data, because invariant tests depend on observations only through maximal invariant statistic. So there is a reduction in data. In last course, you had also seen that there is a reduction in data through sufficiency. So now the natural question arises, if I reduce the data first through sufficiency and then see, so the sufficient statistic will belong to certain class of distributions, and suppose that turns out to be invariant, my testing problem turns out to be invariant, then the test which I get, so the test which I get first applying the sufficiency and then invariance, is that optimal test the same as the test which I get by directly applying the invariance? And the answer is no. In general, it may not be, but in most situations which you will encounter in this course, especially wherever these group of transformations are part of a Euclidean space. So for example, in the location case, we saw that GC of x plus c. So each GC could be characterized by a C in real line. So in all those such situations, the two approaches would be the same. So you can first apply the sufficiency and then you can apply the invariance. So let me write down this as a remark. So in general, UMPI alpha, so UMPI alpha test based on sufficient statistic. So that means I first consider sufficiency and then consider an invariant test based on that, is not same as UMPI alpha test. Based on the whole data. So you can write down sufficient when I say minimal sufficient. Now generally when my G is same as of the type GCs, such that C belongs to B, some set B, where B is a subset of some Euclidean space. So for example, in the case of location x plus C, scale C times x1. So each GC is characterized by a C which is a subset of R above equality holes. Equality holes above. Not a very good English, but I guess it conveys the equality holes above. So that means in the transformations which we have been considering in this course, you can first apply sufficiency and then get the invariant test. based on sufficient statistic, that would be the best test provided the invariant test exists. So now we'll do a result which will give you a relationship between UMPI alpha test and UMPU alpha test. And what it suggests is that if UMPI alpha test exists, then UMPU alpha test would be same as UMPI alpha test, provided UMPU alpha test is invariant. So that is what we do in the next result. So theorem, consider a testing problem So consider a testing problem that is invariant under a group of transformations G. First, if phi star is UMPU alpha test, then phi star is unbiased. So that means every UMPU alpha test, provided it exists, is unbiased. Sorry, UMPI alpha test. So every UMPI alpha test, provided it exists, will always be unbiased. Now, if that is the case, then what happens? So that means UMPI alpha test would be unbiased. So that means its power function would always be less than or equal to power function of this, because it is UMPU alpha test. If phi double star is UMPU alpha test, so that means power function of this would be less than or equal to power function of, would be always be less than or equal to power of UMPU alpha test. But if UMPU alpha test is also invariant, then power function of any UMPU alpha test would be less than or equal to power function of UMPI alpha test. Because any UMPI alpha test, UMPU alpha test is also invariant. So that what it suggests is, if your UMPI alpha test exists and UMPU alpha test is also invariant, then the two have the same power function. So let phi star be an UMPI alpha test. So that means it assumes that it exists. Then only you can talk about that, let phi star be an UMPI alpha test. And let phi double star be an UMPU alpha test. That is also invariant under G. Then phi star and phi double star have the same power function. For every f belonging to P. The proof is almost straightforward. Phi star is UMPI alpha. That means it has a label alpha. So that means expected value of f of phi star x would always be less than or equal to alpha for every f belonging to P0. Now consider the no data test which always rejects H0 with probability alpha for every x. So I consider a test phi naught, which is a randomized test, which irrespective of what observation you observe, it always rejects H0 with probability alpha. Is this an invariant test? Certainly it does not depend on data. So phi naught of x is same as phi naught of gx, which is same as alpha. This implies that phi is invariant and has level alpha. Why? Because expected value of phi naught x is same as alpha for every f, in fact. So for every f belonging to f0, p0 it has. So phi is invariant and it has a level alpha, and phi star is UMPI alpha, so that means the power of phi star would be bigger than or equal to power of. So this implies that EF of phi star x would always be greater than or equal to EF of phi 0x, and power is expected value of power function for every f belonging to P1. Why? Because this is due to the fact that phi star is UMPI alpha and phi naught is any invariant test of level alpha. So what does that mean? That means EF of phi star x is always greater than or equal to EF of phi 0x is always alpha. It does not depend on data. So for every f belonging to P. So what do you have? Power of phi star is always greater than or equal to alpha. It is of level alpha. So power is always greater than or equal to size, which implies that phi star is unbiased. So any UMPI alpha test would always be unbiased. Now, so the second part is always trivial. So let us look at using 2. What do you get? Phi star is UMPI alpha. So phi star is unbiased. And has label alpha. Label alpha is just from this because it is UMPI alpha means that it has a label alpha. And from the first part it follows that it is unbiased because any UMPI alpha test is unbiased. So phi star is unbiased and label alpha, and phi double star is UMPO alpha. So what does that mean? Thus, power of UMPO alpha test, which is phi star x, would always be greater than or equal to EF of phi star x for every f belonging to P1. All right? Now you also know that phi double star is also invariant under Z, and it also has a label alpha. Also, by hypothesis, phi double star is invariant and has label alpha. And you know that phi star is UMPI alpha. So power function of phi star would be greater than or equal to power function of any invariant test of label alpha. So thus, EF of phi star x would always be greater than or equal to EF of phi double star x for every f belonging to P1. Now I combine these two to get that you have equality over here. That means they have the same power function. So this is the relationship between UMPI alpha and UMP alpha test. So what this above theorem suggests that if UMPI alpha test exists and UMPO alpha test exists and UMPO alpha test is invariant, then UMPO alpha test would be nothing but UMPI alpha test. So let me write down this remark, which could be very useful in many situations. If UMPI alpha test exists, so if we can show the existence of a UMPI alpha test, then any UMPU alpha test which is unbiased would be a UMP alpha test. Then any UMPU alpha test that is invariant is UMPI alpha test. All right, so to see a simple application of this remark or the last result, let us consider some situations where I know that UMPU alpha test exists. So let us consider a situation where U uniformly most powerful does not exist, but uniformly most powerful and biased test exists. So what you have is, let us consider x1, x2, xn, IID normal mu sigma square, where theta, which is mu sigma square, belonging to R cross 0 to infinity, capital theta, is unknown. Sigma naught is a fixed positive constant given to us. And suppose you have to test the hypothesis H naught, that sigma square is greater than or equal to sigma naught square, H1 sigma square is less than or equal to sigma naught square. Now, if you recall, this is the case covered under exponential family, because what you can do is you can write down f theta x as 1 by sigma root 2 pi to power n e to power minus 1 by 2 sigma square summation xi minus mu whole square. What I do is I replace it into two parts, because I want to keep some statistics with only sigma square. So I subtract x bar so that with sigma square I can get x bar square. So this is same as 1 by sigma root 2 pi to power n e to power minus 1 by 2 I sigma square summation I is equal to 1 to n xi minus x bar whole square plus n by 2 sigma square and x bar minus mu whole square. So you can see the theory of our unbiased test which we get. You can get a UMP or IU alpha test by one of those results which we did. You can take that as an exercise. And then, because of independence of x bar and this, so what you get is UMPU alpha test phi naught x, which is same as 1. You are rejecting for larger values of sigma naught square, so that means larger values of summation xi minus x bar whole square. By sigma naught square is greater than chi square n minus 1 alpha. Reject H naught, so then when it is smaller, 0 otherwise. And what is this chi square n minus 1 alpha? So that size is alpha, so this is a chi square n minus 1 PDF. So probability of rejecting H naught, that means probability of this greater than chi square n minus alpha under H naught should be alpha. These are chi square on n minus 1, so that means this quantity should be same as alpha. This point is chi square n minus 1. Now this problem, a suitable group of transformations is G of A, B, A positive, B belonging to R, and G of A, B, x1, x2, xn is same as A x1 plus B, A xn plus B. So can you say that this test is unbiased. This is certainly unbiased because UMPU alpha test, that is how you obtain. Try to use that result to prove that this is a UMPU alpha test. Is this test invariant? For this to be invariant, phi naught of AX1 plus B, AX2 plus B, AXN plus B should have been same as phi of X1, X2, Xn. But when I apply AX1 plus B, AX2 plus B, AXN plus B, BB gets cancelled, A comes outside. So it looks like this is not invariant under AX plus B. Is it invariant if I take A to be 1? That is also a group of transformation. Is it invariant under X1 plus B, X2 plus B, and Xn plus B? The answer is it would be invariant under that test. The question is this UMPU alpha test under, is this a UMPU alpha test? This is also a UMPU alpha test. So this would be UMPI alpha test under the transformations GCX, which is a location set of transformations, GC of X1, X2, Xn as X1 plus C, Xn plus C. So this is not invariant under. So finding UMPI alpha test under affine group of transformations I don't get from the last result. Because here I get a UMPU alpha test which is not invariant under affine group of transformations, rather it is invariant under location invariant transformation, location group of transformations. So we'll talk about all this more in the next module. So mainly we'll discuss the relations between sufficiency, invariance, unbiasedness, UMPU test and UMPI alpha test, what is the relationship, and so on. So this is all for today's module, and thank you very much.